For this entire unit up until yesterday, we've considered light, or EMR in general, to be a wave. In fact, on the very first day of this unit, we expressed 4 different properties of waves that are exhibited by EMR: refraction, diffraction, interference, and polarization. We're not throwing that away. We're still abiding by the principle that EMR is a wave. But if we look at an experiment that was performed in 1887 by Heinrich Hertz, and that was explained 18 years later by Einstein, we realize that light isn't just a wave, but light is also a particle. If you remember yesterday, we saw that the photoelectric effect is this phenomenon whereby when light strikes something, usually a metal, not always, but usually a metal, then an electron or electrons is or are sometimes ejected. Hertz and his contemporaries noticed that if the electrons weren't being ejected, we could change the type of EMR to maybe get the electrons being ejected. But that didn't agree with classical theory. Classical physics predicted that it wouldn't be the type of EMR that would cause the electrons to be ejected. Rather, it would be the amount of EMR that would cause the electrons to be ejected. If we had a stronger flashlight, a brighter flashlight, then that might cause electrons to be ejected because it was more light, more energy. Or if we just had a weaker flashlight and shone it on the surface for a longer period of time, that might cause the electrons to be ejected because, again, that's more light. But that didn't work. That didn't match up with the observations that were made. The observations showed that no matter how long you shone the light for or how much of it you shone, if EMR wasn't causing electrons, then EMR wasn't going to cause electrons. If you remember our demonstration a couple of days ago, we threw one piece of paper at Connor. One crumpled up piece of paper didn't cause the electron to be ejected. 25 crumpled up pieces of paper didn't cause the electron to be ejected. If we were below a certain frequency of EMR or below a certain energy, nothing was going to happen ever. So classical theory didn't explain the observations that were made. Einstein comes along in 1905 with this fancy photon theory. If you remember, photon theory says that light exists, sure, as a wave, but light also exists as this particle. And the energy of this particle or photon of EMR is equal to HF or HC over lambda. A photon, by the way, what do we define a photon as? Like loosely as a particle of light, right? But the real definition is? Yeah, it's a quantum of energy. A quantum of energy or a particle of light called a photon has an energy equal to HF or HC over lambda. You can see here, first of all, the wave-particle duality of this. This is the energy of a particle of EMR, but yet it's related to the frequency and the wavelength, 2 wave properties. So the wave-particle duality of this. Secondly, you can see that the energy isn't related to how much of this EMR we have. The energy is related to the frequency and therefore the wavelength of the EMR that we have. That explains beautifully the observations that were made with the photoelectric effect. Remember what we said. Hertz noticed, he knew that it was the type of EMR that would cause emission, not the amount of EMR. He's going to explain why. If we look at this equation, Einstein's equation here, we can see that the type of EMR will affect the amount of photoemission because the type of EMR, which is the frequency, is directly related to the energy. In other words, if we have a higher frequency of EMR, we have a higher energy of EMR, and that's what causes emission. Does that make sense? You can see here by this equation and by the observations that were made that if we have a frequency of EMR that is below a certain value, then the electrons are not going to be ejected. That frequency we call the threshold frequency. We're going to assign a symbol of F0 to that. The threshold frequency, the minimum EMR frequency necessary to eject an electron. If the frequency of the photon, if the frequency of your photon is less than the threshold frequency, F0, what's going to happen? Nothing. if the frequency of your photon is above the threshold frequency, at or above the threshold frequency, what's going to happen? The electrons are going to be ejected, right? Electron or electrons are going to be ejected. Now, we also have a term that kind of goes along with that. It's called the threshold wavelength. The threshold wavelength is the maximum wavelength necessary to eject an electron. We assign a symbol of lambda max to that. If you can imagine if frequency and wavelength are inversely related to each other, if you have a minimum frequency, you got to be above a certain frequency, well, then you better be below a certain wavelength. So we're going to say lambda max is the max wavelength, the maximum wavelength necessary to eject an electron, which means that if your photon frequency, if your photon wavelength, I should say, is above the maximum wavelength of the photon, then we're going to say that no electrons will be ejected. But if your photon frequency, or wavelength, I should say, is below the maximum wavelength, then electron or electrons will be ejected. So you need to be below a certain frequency, you need to be above a certain frequency to cause electrons to be ejected. You need to be below a certain wavelength. Both of those result in having an energy that is big enough to cause electrons to be ejected. Yep?
Is there actually...
Now, the work function goes along with this. The work function is the minimum energy necessary to eject an electron, which corresponds, if we have the minimum energy necessary to eject an electron, it corresponds to the energy that's used up in the process of ejecting the electron. Okay, if I go to 7-Eleven to buy a Slurpee costs $2.19, right? We talked about this yesterday a little bit. If I go to 7-Eleven to buy that Slurpee, the minimum money that I need to buy a Slurpee, which will loosely translate to the work function, is $2.19. Well, that's because the money that gets used up in buying the Slurpee is $2.19. So the minimum money necessary is equivalent to the money that gets used up in the process of buying that Slurpee, okay? The minimum energy necessary to eject an electron, or the work function, corresponds to the energy that gets used up in the process of ejecting the electron. Now, we assign an equation to the work function. The work function, or the minimum energy necessary to eject an electron, is equal to h times the minimum frequency. Or we could say it's h times c over the maximum wavelength. I'm going to square off these two parts of this equation because those two parts are on your data sheet. The last part isn't. We could figure that out, right? We know that E is equal to HF equals HC over lambda. So if on our data sheet it says W is equal to HF0, then you can imagine then that it's also going to be HC over lambda max. If the work function, if the energy of your photon is less than the work function, then nothing happens. If the energy of your photon is greater than or equal to the work function, then something happens. Electron or electrons are ejected. Now, let's assume that electrons are ejected. Let's assume that our frequency of our photon is above the threshold frequency. Or we could say that the wavelength of the photon is below the threshold wavelength. Or we could say that the energy of our photon is above the work function. Okay, any one of those three scenarios here, let's say that electron or electrons are being ejected. If that's the case, and we increase the frequency even more, or we decrease the wavelength, or we increase the energy even more, then what we're going to get here is not more electrons. It's one photon, one electron, 20 photons, 20 electrons. Increase the frequency even more than we already have that's causing electrons to be ejected. It's still going to be a 1-to-1 ratio. But now what we're going to do is cause more energetic electrons to be ejected. So think about that, right? I have a photon that has an energy of 10. That's sufficient to cause an electron to be ejected. Now I have a photon with an energy of 15. Well, that's sufficient to cause an electron to be ejected as well. But it has more energy to provide to the electron. So now the electron that comes out of it is going to have more energy, right? Because I pumped more energy into it. It's still one electron for one photon, but it's a more energetic electron because it was a more energetic photon. But if I have more photons, then I'm able to produce more electrons. I'm more able to eject more electrons. Just a couple more terms that you didn't see yesterday. Stopping potential, and then this conservation of energy thing that we'll end up using to derive an equation. Stopping potential, this isn't really a photoelectric effect term per se. If we're talking about stopping potential or stopping voltage, two terms that mean the same thing, given by the symbol V stop. So electric potential, the electric potential difference is the electric potential required to stop an electron that's already been ejected. The electric potential required to stop an electron that's already been ejected. So the electron has been ejected because the photon frequency was above the threshold frequency. How much above? Whatever. Doesn't matter how much above. Doesn't matter how many we have. How much potential difference is required to stop the electron once it's already been ejected? It's analogous to saying the car is driving, or the car is rolling along the flat surface, and then we got a hill. How much hill, what's the height of the hill required to stop the car? Right? As the car rolls up the hill, it's going to slow down and stop. How high of a hill do we need in order to stop the car? What electric potential difference do we need in order to stop the electron that's already been ejected? We're going to define this as the electric potential, or we could say it's the voltage required to stop dead in its tracks an already ejected electron. Now, this electron, as it's released from the metal surface, or whatever it is that it's released from, has a certain energy, and that would be in the form of kinetic energy. We're going to call it EK max, because we don't actually know how much energy it has. We just know how much it could possibly have, the maximum possible energy that it could possibly have. Well, that's going to be equal to 1/2 mv squared, right? As this electron is moving as a result of being released from this metal surface, it's going to have kinetic energy equal to 1/2 mv squared. That's like the car rolling along the horizontal surface. But as the car starts going up the hill to slow down and stop, that kinetic energy gets converted to what? Yep. Potential energy, right. That's what happens here as well. As this electron has been released, it has kinetic energy, but as this potential difference is applied to it, it slows down and stops. So we're going to say kinetic energy at the bottom of the hill ends up being converted to potential energy at the top of the hill, except it's QV potential energy rather than MGH potential energy. Now, I'm going to just off to the side here change the order of this. I'm going to say EK max is equal to QV, that should say QV stop, not QV final. I mean, really, it's QV final, but corresponds to the stopping potential there. The reason I changed the order of it is because this part of the equation appears on my data sheet, and the last part, the 1/2 mv squared, doesn't, at least not along with this stuff. It appears earlier on in your data sheet, but not with this. The only reason I expressed it in this order, you could see where that comes from, right? Why 1/2 mv squared is equal to QV stop. So once an electron has been ejected, it's got a certain kinetic energy that ends up being converted to potential energy. So we're going to say that EK max, this is what it had when it was released, ends up being equal to QV stop. This is what it has after it's been stopped, after the car has gone up the hill. Finally, there's one more equation that we're going to see here. It comes from law of conservation of energy, which you did last year in Physics 20. The law of conservation of energy says that the energy at the initial point is equal to the energy at the final point, right? You can't create or destroy energy. You can convert it back and forth, but you can't create it or destroy it. If we look at conservation of energy in the context of the photoelectric effect, what is it that has the initial energy? In the beginning, what type of energy did we have? We had light. In the beginning, before anything happened, we had light. And God said, let there be light. and there was light. In the beginning, there was light. H times F is the initial energy. What's the final energy? After all this is over, what has the energy? It's kinetic energy of the electron, right? The electron has been released. So we're going to say the initial energy, that is the energy of the photon, is equal to the final energy of the electron. We're going to call it EK max, because we don't actually know exactly how much kinetic energy it has, rather just how much it could possibly have. But wait a second, those aren't equal, because we know that we have energy that's used up in the process as well, right? What's that called? The energy that's used up in the process. If you don't remember what that's called, do a little work and go back to your notes and look it up, because we talked about that earlier. What's it called? It's called the work function. So what we're going to say is EI, the initial energy, is equal to EF plus the energy that gets used up in ejecting the electron. So if we go back to our Slurpee analogy for a second, if a Slurpee costs $2 and I go down there with $2.25, if my initial energy is $2.25, the final energy is 25 cents, because that's what I come out of the store with, right? 25 cents. I add to that the money that gets used up in the process of ejecting the Slurpee or of buying the Slurpee, which is $2. So $2.25, what I start with, is equal to 25 cents, what I end with, plus the money that gets used up in the process, which is the $2. The energy that I start with is equal to the energy that I end with, plus the energy that gets used up. The $2.25 is equal to the 25 cents plus the $2 that get used up. Now I'm going to star this equation for a couple of reasons. One, because it's really important. You're going to use this equation often. There's 8 questions on a worksheet that you're going to start working on in a few moments. We're going to use this equation. The other reason I'm going to start is because it does not appear on your data sheet. I'm not sure why exactly. I think it doesn't appear on your data sheet because they want you to recognize that it comes from the law of conservation of energy, and they want you to be able to figure it out from the law of conservation of energy. You can do that. If you want, you can absolutely figure out the $2.25 that I went down with is equal to the 25 cents that I'm left with plus the $2 that I used up. You can figure it out, or you can just remember that equation. In the end, make sure you can do one of the two, because it is one that for sure you're going to use on your unit test, and I'm 99.9% sure you're going to end up using it on your diploma exam. Again, despite the fact that it's not on your data sheet. Here's your first example. Since the work function of a particular metal is 4 electron volts, I think it was Zach that talked earlier about having different threshold frequencies, different work functions for different metals. Yeah, absolutely, absolutely. The work function of this metal is 4 electron volts. For some other metal, it's higher. For some other metal, it's lower. Okay, different work function, different threshold frequency for every different material. Now, we see 2 photons incident upon the metal, one with a frequency of 9.9 times 10 to the 14, one with a wavelength of 3.5 times 10 to the minus 7. Are each of these photons going to cause emission? Maybe one is, maybe one isn't. Maybe they both are. Maybe neither one is. How are we going to go about solving this? Well, what I want to do first here is just refresh your memory as to what equations I have at my disposal. What's in the toolbox for us to do these photoelectric effect questions? We have E is equal to HF and is equal to HC over lambda. Both of those equations appear on our data sheet. We also have W is equal to HF0 is equal to HC over lambda max. The first part of that appears on your data sheet, but not the second part. Then we have EK max is equal to QV stop is equal to 1/2 V max squared. The first part of that is on my data sheet. And then finally, we have that last one that was derived from the law of conservation of energy that says HF is equal to EK max plus W. We're not going to square off any of those because that doesn't appear on our data sheet. No part of it appears on our data sheet. All right, there's our equations that we're allowed to use. How are we going to go about solving this question? Recognize first that we have two different photons, and we want to find if each of them will cause emission. So this is really two problems, right? Let's say we have our green problem and we have our black problem. Our green problem is when we have a frequency of photon of 9.9 times 10 to the 14 hertz. And a work function of 4.00 electron volts. There's two ways that we can tackle this problem. One, let's solve for the energy of this photon. E is equal to h times f, which is 6, what value of Planck's constant do you want to use here? Yeah, let's use the electron volt one, right? You could use joules, but if you do, you have to convert this to joules, right? 4.14 times 10 to the negative 15 eV times seconds times 9.9 times 10 to the 14 hertz. That gives us 4.1 eV. So the energy of this photon is 4.1 eV. Are electrons going to be ejected here? Yes. The answer is yes, because the energy of your photon is above the work function. Does that make sense? You get a photon that's 4.1. All you needed was 4.0. We're going down to 7-Eleven with $2.10. We only needed $2. Are we going to end up with a Slurpee? Yes, because we were above the minimum amount necessary to get a Slurpee. Now, there is another way to do this as well. We could have said, do you have an idea for it? Okay. Yep. Absolutely. F0 is equal to W over Planck's constant. Now, I didn't actually figure out what that is myself, because that's just not the way I did it when I was working on this myself. So I don't know what the number is. But if we figure it out, somebody figure this out while I'm writing this. 9.6 times 10 to the 14 hertz. Okay. So you could look at it this way and say, look, the threshold frequency is 9.6. What do I have? 9.9. Am I above the threshold frequency? Yes. And electrons will be ejected. So I don't care which way you do it. Either way, you don't need to do it both ways. Right? One way is fine. Find the energy and compare it to the work function, or find the frequency and compare it to the threshold frequency. Got it? Now, the other one's going to be our black problem. This is the one where my wavelength is 3.5 times 10 to the negative 7 meters. My work function is still the same. Connor, which way do you want to do this one?
I did that.
Okay, so we could solve for the energy saying E is equal to hc over lambda. If we do that, using h as 4.14 times 10 to the negative 15, we get an energy here of 3.5 EVs. But what did we need? 4. This is like going, Slurpees at 7-Eleven is $2. It's like going to 7-Eleven with $1.75, right? We're going to get a Slurpee? No Slurpees ejected because the energy of my photon is less than the minimum energy necessary. It's less than the threshold or the work function. Now, the other way you could do this is to say E is equal to hc over lambda max. Therefore, lambda max is equal to hc over E. And I don't know what you end up getting for lambda max there, because I didn't do it that way. But whatever value you get, lambda max, the wavelength of my photon will be greater than lambda max. And that will cause no electrons to be ejected because our lambda is too high. One more example for us today, and then that'll be it. This one says the wavelength of EMR incident on a photoelectric surface is 5 × 10⁻⁷ meters. What's the maximum speed of the electron if the work function on the surface is 0.5 electron volts? Let me just, before I write down givens, paste those equations that we're allowed to use here. And now let's write down the givens that we have associated with this question here. We have a wavelength of 5.0 × 10⁻⁷ meters. We have a work function of 0.50 EVs. And we're looking for the maximum speed, Vmax. I'm going to give you 5 seconds, and I'm going to start counting in a moment, 5 seconds to come up with the equation that we're going to use to solve this problem. Starting now. 1, 2, 3, 4, 5. Who's got it? Nobody's got it. Okay, that's okay. That's because we're going to use for this problem the equation that I call the 5-second equation. The 5-second equation. If you can't come up with an equation in 5 seconds or less after writing down givens, then it's probably going to be that last one that you're going to use. Not for sure, but 90%. Okay, if it's going to be one of these first 3 equations, like if it's going to be this one, or this one, it's quite likely that you're going to come up with the proper equation to use pretty quickly. If you don't, then try that last equation, what I call the 5-second equation. So let's do that now. Let's write down that 5-second equation. HF is equal to EK max plus W. But wait a second, it doesn't look like that one's going to fit either. Because I don't know what the frequency is, right? But look, I know the H times F is the same thing as saying HC over lambda. So let's replace HF with HC over lambda. Looking for Vmax, I don't know what that is, but I know that Vmax is related to the maximum kinetic energy. So let's replace kinetic energy with 1/2 mv max squared. And we've got the work function. So we can see that we changed this equation quite a bit, but that's what makes it so versatile. And that's what makes it so difficult sometimes to see which equation we're going to use. If you end up having givens that don't look like they fit anything, it's probably because you're going to use some altered form of the 5-second equation. Does that make sense? If you come up with an equation within 5-10 seconds, use it. If you don't, then use the 5-second equation, or at least try the 5-second equation. Now, let's sub in our numbers here. What value of H are we going to use? 6.63 joule seconds or 4.14 electron volt seconds? You're going to love me now. I use that term sarcastically. Love. You're going to hate me now is what I really mean. Here's the thing. Most times you can use joules or electron volts, whatever you want. This is an exception. Whenever you introduce 1/2 mv squared or QV, you must use joules. So I'm using 1/2 mv squared here. I got to use joules. If I had left this as EK, I would have been okay with the electron volts. But as soon as I replace it with 1/2 mv squared or QV stop, I got to use joules. Now, does that confuse anybody? No? That would me. If it confuses you, then just use joules all the time. Joules always works. Electron volts usually works. Joules always works. If you wanted to use joules for any question, sometimes you just got to convert electron volts to joules. That's all. That's what we're going to have to do in this case, in fact. Let's start subbing in some numbers here. Let's say 6.63 times 10⁻34 joule seconds because we're using 1/2 mv squared. 3 times 10 to the 8 is C. Divided by the wavelength is 5 times 10 to the -7. The mass is 9.11 times 10 to the -31 times V squared. Plus the work function. What's the work function? We know that 1 EV is 1.6 times 10 to the -19 joules. Therefore, 0.5 EVs is X joules. I think it's 8.0 times 10 to the -20 when we do the math there. So get this number and take this over by subtracting. then multiply by 1/2, then divide by 9.11, and then square root. Let's do that on the calculator just to make sure that you guys can follow along with that. 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 5 times 10 to the negative 7. Let's subtract from that the 8 times 10 to the negative 20. Now let's multiply that by 2, divide by 9.11 times 10 to the minus 31, and then let's square root that. Do we get a value of 8.4 times 10 to the 5? Is that a reasonable speed? Yeah. 10 to the 4, 10 to the 5, 10 to the 6, yeah, that's reasonable. Yeah.
Why is it like a maximum speed?
Why is it maximum speeds versus just speed?
Like, why, like, when one technically is on a speed of light, still cause it to turn like that?
Well, be careful here. The maximum speed is the maximum speed of the electron that's been ejected. The speed of the photon is 3 times 10 to the 8.
Oh, this is the one that got ejected?
Yes, this is the electron that's been ejected. The photon, right, the photon that strikes it is going the speed of light. But the electron, it gets ejected with a certain amount of energy. We can't actually predict the exact amount of energy that it has. We can only predict the maximum possible amount of energy that it has. So therefore, we can only predict the maximum possible speed. When we calculate this, we're not saying this is how fast it's moving. We're saying this is how fast it could be moving if there's no energy loss due to other factors.